It all begins with something most people never think twice about: a roll of metal. Not just any metal, aluminum foil, but not the kind you'd use in your kitchen. This foil is destined to become part of the powerful little device that sits quietly in backpacks, pockets, or desk drawers, waiting for the moment a phone hits 1%. This is the positive electrode in a lithium battery, the very heart of a power bank. Before anything takes shape, the aluminum foil is carefully coated. It's not just dipped in any liquid. This mixture is engineered to the molecule. It includes active materials like ternary compounds and lithium manganese oxide. Conductive agents help electrons move freely, binders hold the structure together, and solvents keep everything just the right consistency. The mixture is spread evenly across the aluminum using a precision coating machine, forming a sticky black film. Once coated, the foil goes through a drying process where all that solvent evaporates, leaving behind a perfectly smooth layer of electrode material. It's during this drying phase that the real transformation begins. The same coating process happens for the negative electrode too, except copper foil is used instead of aluminum. And that slight change in material makes a massive difference when it comes to battery chemistry. After drying, there's no time to waste. The coated electrodes are passed through a roll press. The goal here is to squeeze the material thinner and denser. That not only saves space, but ensures a consistent structure, which is crucial for performance. A properly pressed surface reflects light, almost like a mirror. That shiny finish? It's a sign the electrode is ready for the next phase. Now the material is trimmed, or what they call slitting. Picture these wide-coated sheets being sliced into narrow, clean strips, each one ready to be turned into the inner workings of a battery. The edges are flawless, the waste is vacuumed up and recycled. It's clean, efficient, and surprisingly satisfying to watch. Once the slitting is done, the next step is tabbing. Here, small metal tabs are welded onto both the positive and negative electrodes. Aluminum tabs for the positive side, nickel tabs for the negative. These tabs will eventually be the connection points for the power bank's circuit board. But they're not just tacked on. Each weld has to meet specific tensile strength standards. If it's too weak, the battery won't survive assembly. If it's too strong, it risks damaging the thin electrode materials. It's all about balance. The machines performing these welds are tuned to microsecond precision, delivering just enough energy to create a bond without burning through the material. In a single shift, thousands of tab welds are performed, and each one must be flawless. Sensors monitor the current, pressure, and temperature in real time, flagging even the smallest anomaly. Sometimes a tab weld may appear perfect on the surface, but internal resistance tells another story. That's why additional electrical tests are often run after this step. Tabbing also sets the stage for how well the battery integrates into the larger power system. If the connection points are even slightly misaligned, it can cause serious issues during assembly. Operators often work under magnifiers, using cameras and screens to guide placement down to the millimeter. There's a visual rhythm to this stage. Clean, consistent welds lined up like stitches on fabric. Each spark from the welder is a tiny burst of precision engineering. Depending on the battery format, the tab length and position might change, but the core principle remains the same: strength without compromise. Sometimes the tabs are folded or bent to prepare for the next stage, and that bend needs to be perfect. Too sharp and it could crack under stress. Too loose and it might not fit properly into the final pack. In high-capacity designs, dual tab configurations are sometimes used to distribute current more evenly. That adds another layer of complexity, but also improves performance. Engineers often revisit the tabbing stage when optimizing for efficiency or improving battery longevity. Even the tab material itself is carefully selected for conductivity, durability, and cost. It's a small part of the battery, but a vital one. In many ways, the tabs are the silent heroes of energy transfer. And once this precise dance of welding and alignment is done, the battery is finally ready to be shaped into the energy core that powers a modern device. With tabbing completed, it's time to build the core of the battery. Using an automatic winding machine, the positive and negative electrodes are carefully wound together with a separator sheet sandwiched in between. The separator does exactly what it sounds like. It keeps the two electrodes from touching each other directly. If they ever did, it could lead to a short circuit, or worse, a fire. Winding this way ensures compact, high-capacity cells that are safe and reliable. But winding isn't where the checks stop. The wound battery cores go through X-ray inspection. And yes, that means the inside is scanned like luggage at an airport. This step ensures the layers are perfectly aligned and free of defects. Any core that doesn't meet the standard is removed before it causes problems later. Once the internal structure is cleared, the battery core gets its outer layer. It's inserted into an aluminum plastic film casing. A heated copper mold seals the edges to keep everything airtight. This film isn't just for looks. It's flexible, strong, and lightweight, perfect for the slim, modern design expected in portable tech. But the battery isn't alive yet, not until it's baked, literally. These cells are placed in a high-temperature vacuum environment. The goal here is to remove every last trace of moisture from inside the cell. Even microscopic droplets can mess with performance or create long-term safety risks. After baking, it's finally time for one of the most important steps: electrolyte injection. The electrolyte is a special liquid that allows lithium ions to move between the electrodes. Too much or too little, and the battery won't work as intended. So every battery is weighed before and after the injection. It's not a guess, it's science. Only the correct amount will ensure proper function. The electrolyte acts like the bloodstream of the battery, enabling the essential chemical reactions that store and release energy. But it's also highly sensitive. The environment has to be perfectly controlled. Humidity levels, temperature, even air quality, all of it matters. During injection, the battery cell is placed in a sealed chamber to minimize exposure to air because the electrolyte can react negatively with moisture. It's why even a tiny air leak can ruin a cell. The machinery used for injection has to be incredibly precise. We're talking about fractions of a gram here, micro adjustments to ensure just the right balance. After the injection, each cell is immediately reweighed to confirm the added volume. If the weight's off by even a fraction, the cell is flagged for review. The process isn't rushed. The goal is saturation, not speed. Some manufacturers even allow a short rest period after injection, letting the liquid naturally soak into the internal layers. This helps reduce trapped air and ensures better contact with the electrodes. The chemistry inside is delicate, and even distribution is key. Uneven electrolyte levels can cause performance inconsistencies or premature failure. The liquid itself varies depending on battery type, but it usually includes lithium salts and organic solvents, engineered for fast ion mobility and stability. There's a whole science around optimizing this formula for different battery uses. High-drain applications need faster ion transport, while long-life batteries need better stability. The containers used to hold the electrolyte are often nitrogen-sealed to avoid contamination, and operators wear gloves, goggles, and full suits to handle it safely. Even a small spill can be hazardous. Once inside the cell, the electrolyte doesn't just sit there. It becomes part of the chemical symphony. It must fill every crevice between the tightly wound electrodes, acting as a medium that makes the battery come alive. This one step, so quick in real time, can determine how well a battery performs for months or even years. That's why it's treated with the same seriousness as a launch countdown. When done right, the cell is fully charged, not just with liquid, but with potential. Once the electrolyte is in, the battery enters its aging phase. No, it doesn't mean sitting on a shelf and collecting dust. It's placed in a controlled high-temperature environment to allow the electrolyte to fully soak into the internal materials. This step helps improve the long-term performance and stability of the battery. Next up is formation. This is when the battery is charged for the very first time, and that first charge is crucial. During formation, a stable SEI layer forms on the electrodes. This layer acts like a shield, protecting the battery from degradation while allowing ions to pass through during charging and discharging. Without this step, a battery wouldn't last very long. Before final assembly, there's a final gas extraction step using a vacuum. Any residual gases are pulled out of the cell to ensure nothing contaminates the battery over time. After that, the battery is trimmed, removing excess material around the edges. This ensures the battery is exactly the right size to fit into a power bank. But performance matters most. So each cell goes through capacity testing. They're charged and discharged to measure how much power they actually hold. Cells are grouped by their capacity levels to ensure consistent performance in the final product. If one cell performs worse than the others, it's removed. Only the best make it through. Next comes the OCV, or Open Circuit Voltage, test. This checks the self-discharge rate. Batteries are left untouched for a set period, and the voltage drop is measured. A healthy cell will hold its charge. If it doesn't, it's flagged and pulled from production. At this point, you'd think the hard part is over, but the real show is just about to start. Now it's time to assemble the power bank itself. Inside the BlueTimes facility, these cells are lined up for a final round of checks. They go through visual inspections, voltage checks, and safety validations. Then 2 or more battery cells are paired together to form a single battery pack, increasing the overall capacity of the power bank. And this is where things really start to spark, literally. Spot welding connects the cells using nickel strips. These high-speed welds use intense heat and pressure to fuse the metal together. It's fast, loud, and dramatic, especially when sparks fly, but it's all controlled with incredible precision. These connections must handle both energy transfer and mechanical stress. Once the cells are connected, the brains are added. That means installing the protection circuit, also known as the BMS or Battery Management System. This tiny circuit ensures safety by monitoring temperature, voltage, and current flow. It's what keeps the power bank from overcharging, short-circuiting, or overheating. Without this, using a power bank would be a gamble. Now that the inside is complete, the casing comes next. This isn't just snapped together. An ultrasonic welding machine seals the plastic shell shut. Using high-frequency vibrations, it melts and fuses the case without using glue or screws. The result? A seamless finish that looks clean and feels durable. And once it's sealed, there's no going back. The case isn't meant to be opened. The power bank is almost ready, but it's not official until it's tested. The final device goes through more aging tests to simulate long-term use. It's charged, discharged, dropped, and shaken. And yes, there's even a drop test where the power bank is smashed against a hard surface to make sure it won't break or malfunction under real-world conditions. Only the strongest survive. For branding, there's a laser printing process that adds the final logo or product details. It's clean, fast, and permanent. And just like that, a brand new power bank rolls off the line. Sleek, compact, and ready to charge anything from phones to tablets and beyond. Behind every power bank is a journey of chemistry, engineering, precision, and innovation. And at the center of it all is BlueTimes, a company with over 18 years of experience in building smart, sustainable, and reliable energy solutions. As a leading OEM and ODM partner, BlueTimes doesn't just build power banks. They engineer trust, consistency, and performance. With patented designs, rapid development cycles, and factory-grade precision, their technology helps brands stand out while delivering the power users depend on every single day. From aluminum foil to circuit boards, from baking ovens to drop tests, this process is a reminder that portable energy isn't just about convenience. It's about innovation, it's about safety, and it's about turning science into something people carry in their pockets without ever thinking twice about it. And that's how power banks are made. Don't forget to like, comment, and subscribe for more behind-the-scenes looks into the world of tech, design, and innovation.